So this week we will be looking at intermolecular forces and measuring intermolecular forces via contact angle. So this is really all about understanding the interactions between a liquid and a surface, or two liquids or two surfaces. So intermolecular forces, all intermolecular forces are electrostatic interactions. So that means a positive charge is attracted to a negative charge, positive charges are repelling each other, etc. It's a charged interaction. The strength of the intermolecular forces, and that's between two different molecules, depends on the magnitude of the partial charges. So the difference in electronegativity between atoms within the molecule or the polarity of the bond within the molecule are important here. Some common functional groups that you might see, especially in organic chemistry, are hydroxyl groups, that's the OH group. Methyl group is the CH3 group, so carbon with 3 hydrogens. The R's here represent just the rest of the molecule, okay, typically other carbons. A carbonyl group is a carbon double bonded to an oxygen. A carboxyl group is a carbon double bonded to an oxygen and also an OH group. And an amino group is an NH2 group. So nitrogen with 2 hydrogens on it. If we think about the polarity of each of these functional groups, we can determine, using the change in electronegativity or the difference in electronegativity between any two atoms by taking the absolute value of the electronegativity of each of the atoms and subtracting them. So if we look at the hydroxyl group, we take the electronegativity of the oxygen and subtract the electronegativity of hydrogen, and we see a difference in electronegativity of 1.4. We could do this for the methyl group, and we get a difference of 0.4. We see for carbonyl, we get a difference of 1. For the amino group, we get a difference of 0.9. Now, what does this mean? This difference in electronegativity tells us about the polarity of that functional group. Polarity is a continuum, okay? It's not a this or that, right? But it's really a continuum. And just by convention, anything that's less than 0.5 difference in electronegativity we call nonpolar, covalent bond. Anything between 0.5 and 2 we call polar covalent bond. Anything above 2 is an ionic bond, so that would be, a chlorine with a sodium to make sodium chloride, right? Sodium gives up its electron completely, and you have an ionic bond. So if we look at these differences in electronegativities for these functional groups, we can see that the OH hydroxyl group is polar, the CH3 or methyl group is nonpolar, CO is polar, and amino is also polar. Polarity is a continuum. That's sort of an important point. Let's just compare two of these that are both polar. Okay, if we look at the OH group versus the NH group, they're both labeled as polar, but the OH group has a 1.4, which means it's more polar, and the NH group has a 0.9, which is less polar. Okay. In each of these, the more electronegative atom is oxygen or nitrogen, and the less electronegative atom are those hydrogens. Okay. And that means that the oxygen and the nitrogen have partial negative charges, and the hydrogens each have partial positive charges, right? So the more electronegative atom is pulling electron density towards itself and away from hydrogen. So hydrogen looks like it has less than 1 electron present. Nitrogen looks like it has more than its allotted share of electrons. Because this has a difference in electronegativity of 1.4, that's going to make this separation of charge, or the partial charges here on oxygen and hydrogen, larger, right? Oxygen is more electronegative, so there is a more extreme separation of charge. Here on the nitro group, we have less extreme separation of charge because there's a lower difference in electronegativity between nitrogen and hydrogen, so they're sharing more equally. So what does this have to do with anything? If you remember Coulombs Law, okay, the force, the electrostatic force, is equal to a proportionality constant times the charge on one particle, the charge on the other particle, and the distance between them. So these partial charges that we just talked about on oxygen and hydrogen and nitrogen and hydrogen, those are charges. We can think of those as the charges that would go into Coulombs Law. So if we think about how each of these molecules, one with an OH functional and one with an NH functional, how are these going to interact with another substance, like a substrate, like a glass substrate? Okay. Well, the surface of the glass has OH groups on it. Okay, hydroxyl groups. So if we look at the partial charges here, my molecule hydroxyl has partial negative on oxygen, partial positive on hydrogen. The hydroxyl on the glass surface also has a partial negative on oxygen and a partial positive on hydrogen. My oxygen from my molecule is going to be attracted to those hydrogen, the positive charges on the hydrogens. And my hydrogen on my molecule is going to be attracted to the partial negative on the oxygen on the surface. Now these dotted lines, anytime you see dotted lines, that usually indicates an intermolecular force between two molecules. Okay, so not an attractive force within a molecule, rather between two molecules. So I have this intermolecular force and this intermolecular force. Those are attractive forces of this molecule to the surface, and they can each be described by their own Coulombs law. Okay, so the charge on my oxygen on my molecule and the charge on my hydrogen on my surface, right, and the distance between them is going to have an attractive force. Here, the charge on my hydrogen on my molecule and the charge on my oxygen on the surface, right, those are going to be attracted to each other, and they're going to have an attractive force that's described by Coulombs law. We can do the same thing for the amino group. Okay, the hydrogen on my molecule is attracted to the oxygen on the surface. The hydrogen on my surface is attracted to the nitrogen in my molecule, and they are each described by Coulombs law. So the question is, will the OH group or the NH group interact more with the glass surface? So will this molecule with a hydroxyl be more attracted to the surface than the amino group, or will the amino group be more attracted to the surface than the hydroxyl group? So which will have the stronger electrostatic attraction? Which will have larger forces here? All right, if you think about it, because my charge on my oxygen here is greater than my charge on my nitrogen, then that means that this force between my hydroxyl group and my surface is going to be greater than my amino group and my surface. Also, my positive charge on hydrogen from my hydroxyl group is greater than my positive charge on hydrogen from the amino group. So this force will be greater here between my hydroxyl and my surface than my amino and my surface. So the hydroxyl group will have a stronger interaction with the glass surface. It'll have a stronger electrostatic attraction. So what does that mean? And how do we measure that? Well, one way to measure that is to use contact angle. So this is to look at a liquid, a droplet of liquid on a surface, okay? And if that liquid is water, then we can think about that surface being hydrophobic or hydrophilic, okay? So hydrophobic means it's afraid of water, the surface is afraid of water, and so it's slightly repelling water, okay? Hydrophilic means it likes water, and it's going to attract water to its surface and hold it tightly. If you have a small contact angle here, water has a strong interaction with the surface, and likely that surface is polar. Okay? If you have a large contact angle, then water is going to have a weak interaction with that surface, and likely the surface has nonpolar functionality. Okay? Now, I should note that this liquid, whatever this liquid is, doesn't have to be water. It could be any liquid or solution, right? You just have to know something about the drop in order to determine the interaction between these two things, or you have to know something about the surface in order to determine the interaction between these two things. And a reminder that polarity is a continuum, and so is hydrophilic, hydrophobic, and interaction measures. Okay, so we could have a hydrophilic surface, and that has a very low contact angle like this. We could have another surface that still has an acute angle, right, but that is larger than this, and we would call that still hydrophilic, but we would say it's more hydrophobic or less hydrophilic than the drawing that's here. So all of those interactions occur on a continuum. So what are you going to be doing in lab? Well, you are going to build a contact angle apparatus. So you're going to use your phone and you're going to look at your surface, and you're going to put a drop of water on a surface, and you're going to measure the contact angle. So you're going to build your own instrument. You're going to optimize your drop image. There's a variety of drop images that you could get. This is a standard that helps you learn how to measure these angles. Okay, but you can see these are actual photos of drops on surfaces that students have taken. And you can see that the quality of that image is widely varying. And so depending on the quality of your image, it will determine how well you can measure that angle, contact angle. So you're going to have to optimize your image quality. And then you're going to investigate surfaces. So we have a variety of metals, we have a variety of glasses, we have a variety of plastics, just a variety of surfaces. And you are going to determine if each of those are hydrophilic, hydrophobic, what is the range? You're going to ask your own question and investigate that this week.